Psychrometric Applications. Here's a problem that we solved in class on Monday, or today, when I'm recording this for Wednesday's lecture. And one thing that I wanted to do was to highlight or summarize some of the key steps, because I feel that following the process you can get a little confused at times. And so if you'll allow me, I'm going to summarize solving this problem where you have let's remind ourselves of the problem. So we have moist air in a rigid closed tank. It's hot, it's high pressure, and it has 40% relative humidity. And then the tank is cooled to a certain temperature. And you're asked to calculate things like the final pressure in the tank, the final relative humidity, final humidity ratio, and the heat transfer during the process. This temperature, in one part we had it at 60 degrees C, and then we changed it so it went from 80 to 60 and then 80 to 40. And we found the results were very different when you go all the way to 40 degrees C, because some of the water vapor condenses. And when it condenses, it takes a lot of heat transfer to condense vapor. So the Q, the answer to part D, was much larger when you went from 80 to 40 versus 80 to 60. So here are the key equations. I'll try and put them in a column format. You had the initial pressure of 400 kPa. Then you had the initial temperature of 80 degrees C, and you're going to every now and then need it in Kelvin using the ideal gas equation. And the relative humidity was 40%. These were all given, true? You can look up the saturation pressure at 80 degrees C, and you find that that's a whopping 47.4 kPa. And then you can calculate, let's say just calculate the vapor pressure initially in the tank, which is the product of the relative humidity and the saturation pressure. So we get that it's right at 19 kilopascal because it was at 40% relative humidity. Then you can calculate the pressure of the dry air initially in the tank. That's the pressure in the tank minus the pressure of the vapor in the tank at state 1, or the initial state. And so it's 381 kPa. And then you can calculate the mass of the dry air in the tank, which is the ideal gas equation: pressure of the dry air, volume of the tank, molar mass of dry air, R bar T. That's an R bar T. And we calculated 9.403 kilograms of dry air. We calculate the humidity ratio initially in the tank, 0.622, the vapor pressure over the dry air pressure, state 1, and that comes in at 0.03094. And then the vapor that's in the tank, using the ideal gas equation, partial pressure of the vapor, the total volume, molar mass of the vapor, 18.02, R bar T, all at state 1, and you get 0.291 kilograms. Okay, how do we then jump and start calculating at state 2? Either state 2 is 60 degrees or 40 degrees. Well, one way to do it is just to go ahead and assume that the vapor all stays in the vapor state. All the water stays in the vapor state. If you do that, you'll find that P2 is equal to P1 times T2 over T1 from the ideal gas equation. Assume it's all ideal gas, air and vapor, initially at state 1 as well as finally at state 2. And you calculate that the final pressure does go down because it's cooling. This is for a temperature of 60 degrees C and 333 kPa. I'll show it also for 40 degrees C. And then what is the saturation pressure, Psat, at 60 degrees C? Well, that is 19.94 kPa. And so the vapor pressure at state 2, assuming it all stays ideal gas, is just like the above equation for the total pressure, PV1 T2 over T1, and it comes right in at like 17.9 kPa. And then the partial pressure of dry air at 2, a similar equation, is 359.5 kPa. So that's the same way that the pressures are changed. If they're always ideal gas, you calculate then the relative humidity, phi2, which is PV2 divided by Psat at 60 degrees. And we find that it's real close to 90%, 89.7%. Okay? If you came in here and changed it for 40 degrees, so T2 was 40 degrees C, and then what is that, 273? That's at I didn't write that down. What is 40 and 273? 313, that's right. 313 Kelvin. What you find is Psat at 40 degrees C would be much, let me look at some of these notes right here. Psat at 40 degrees C,
7.34.
right, much lower. And then when you calculate the relative humidity, you'll find that it exceeds 100%. It can't be all vapor. You can't be all vapor at state 2 if it's 40 degrees C. It can be all vapor if it's 60 degrees C. So let me jump to the Excel file. Maybe the Excel file will make it a little easier to see. So here are kind of the givens, the given, kind of laid out as I read it to you for state 1, 80 degrees C. If you go to 60 degrees C, you end up calculating the relative humidity is about 90%. The partial pressure of the dry air is here. The humidity ratio is the same. It doesn't change. The amount of vapor to dry air doesn't change going from 80 to 60 degrees C. And you can look up the values of use of G and use of G at the different temperatures. Use specific heat for the dry air. Calculate how much it takes to cool the dry air, how much it takes to cool the water vapor. Because there's so much less water vapor, it's a lower amount, and it's 143 kilojoules needs to be removed of heat transfer. 95% of that is to cool the dry air, and about 5% of it's to cool the moisture. Now, it is a small amount to cool the moisture, but look at humidity ratio is about 3%. So it's only 3 kilograms of vapor per kilogram of dry air. So this looks all about right. But what happens if you cool it from 80 to 40? If we try the same process, what you find is that you calculate a relative humidity of 227%. It's impossible. So at that point, you know some of it's condensed. And now you have to figure out how much condensed. So I didn't calculate the rest of this. It's just that I knew the saturation pressure at 60. Whoops, that should say 40 right here. That's a comment. That should be 40. Okay? Let me fix that. Let me hit 40. All right. But let's jump now to this case. So what we do is you say at state 2, it's going to be assumed to be 100% relative humidity. Okay, if you assume that it's 100% relative humidity, then you know that the saturation pressure and the partial pressure of vapor are the same. It's 7.38. So the dry air changes like an ideal gas, like it did in the first case. But the total pressure now is calculated by summing the vapor partial pressure and the dry air pressure. So it actually dropped a little more rapidly than if it would have stayed all in the ideal gas, because some of it condensed, some of the vapor condensed. And you can still see that the mass of the dry air didn't change, but when you calculate the mass that's in the vapor state, it's gone down from 0.298 to 0.1278 kilograms. So there's only 44% of what started out is in the vapor state. And this is the amount of liquid. Just looking at the equation, you take the difference between those two, right? And then that's 56% of the initial vapor. So quite a bit of the water has condensed. And you have to look up use of F for that, temperature of 40 degrees C, use of G for that temperature. And when you calculate the total amount of cooling required, it's a lot higher, 655 kilojoules. And 41% of it is attributed to cooling the air. Cooling the vapor that stays in the vapor state, only 1%, but 58% is associated with condensing the vapor. So going from use of G all the way to use of F. That's a large change in internal energy for that mass that is now in the liquid state. I may have changed some numbers here. I may have gone down to 30 degrees earlier, but here I just went 20 degree increments. So if you go 80 to 60 or 80 to 40, it's a 20 degree change or a 40 degree change. Helps put it in perspective. But the perspective, something to glean is this is a significant amount. And they would call this predominantly the sensible heating or the sensible cooling of the air. This is the latent cooling, or the latent, it's the hidden part. It's due to the phase change. Okay, let's jump back to the lecture. I hope that was worthwhile. I do. So far we've been introduced to two humidities. We have the relative humidity, phi, and the humidity ratio, omega. And both are helpful or useful. This one, goes between 0 and 100%. This one goes between 0 and whatever, and it's units of kilograms of vapor per kilogram of dry air. So two humidities we've been introduced to. Sometimes they'll have different names for humidity ratio. So in older literature, you may have to be careful, but I don't want to introduce too many names for the same term. So this class, humidity ratio, omega. There's three temperatures. Now, the one temperature is what we're going to call the dry bulb. It's the temperature that's read on thermostats in rooms. It's the thermostat, the thermometer on the back porch of your house. It's the thermometer that's inside the stove when you say I want to set it to 350 degrees F. That's the dry bulb temperature, and it just means, just like you say, dry bulb. If you leave off that dry bulb, it's the common temperature associated with the air temperature. The outside, it was 85 degrees yesterday. All right. The next temperature was the dew point. True? The dew point temperature. And so for moist air, you do have two temperatures describing its condition. You have its dry bulb temperature and the dew point temperature. Now, that dew point temperature is going to be less than the dry bulb. That's a kind of tricky concept. And it can be equal to the dry bulb if it's saturated air. If it's saturated air, the current temperature is the dew point temperature. Because if you cool it any more, it's going to dew out. There's one other temperature, and it has two names: the adiabatic saturation temperature, also the wet bulb temperature. And I'm not going to get into a distinction between the two. So what we'll do is we'll show you two things. One is the sling psychrometer, which I have in front of me, as well as we'll talk about the adiabatic saturator. So this is the adiabatic saturation temperature, which is essentially the same as the wet bulb temperature. Okay, so dry bulb, dew point, wet bulb, or adiabatic saturation temperature. All three temperatures help quantify the current conditions of our moist air. And let's say the air is very, very dry. If the air is very, very dry, the dew point temperature goes much below the current dry bulb temperature. And similarly, the adiabatic or wet bulb temperature goes much below the dew point temperature. If it's 100% relative humidity, then this very special case, it's saturated air and the temperature dry bulb is equal to the temperature dew point is equal to the temperature wet bulb, which is the same as the temperature adiabatic saturation. So all three temperatures coexist, or they have the same numeric value for saturated air. Let's talk about the adiabatic saturation temperature. So we consider an adiabatic saturator. It's a well-insulated device that has a chamber in which air can flow into it, and it comes in at a certain temperature and a certain humidity. Okay, we'll talk about omega, the humidity ratio of the incoming air. And it's exposed to freestanding water. That water, you can just think about being in a puddle. And it blows over the puddle, and you can make that puddle much, much longer. How do they draw that? Like this, so much longer, such that it will come out at the end of the chamber. Well, I don't know why my computer doesn't want to work today. Come on now. What did I do to upset him? Do you know what I did to upset my computer? It's so old here. Come on now. Don't give up on me. I'm not drawing.
Did you say please?
Please. Please, let's do it. No.
Can you pause the recorder?
Yeah, but I'm afraid it's going to bomb. See, it's a recording, but we're not getting. I'm not able to write it. Let me try pause. I resume. Oh, I'm going to have to do this. I'm going to have to go ahead and stop. Good. And so it comes out at a lower temperature, and they call it the adiabatic saturation temperature. And it comes out at a different omega prime. Now it picks up some moisture, so omega prime is going to be greater than omega, and the adiabatic saturation temperature is going to be less than the inlet temperature. Now because there's some water that's going to be added to this airstream coming through, that you have to have some makeup water. So there's some mass, m dot liquid that's made up, and there's an assumption in the derivation that this liquid makeup is at the same temperature as the outlet. It comes in at the adiabatic saturation temperature. It really is not a big deal if it's a little off, but what you want to do now is you want to do a mass balance and an energy balance. Two mass balances. One is for the air only. And you find that the mass flow rate of the dry air coming in is equal to the mass flow rate of the dry air going out. And that's not too surprising, and then often you just drop the subscripts in and out. You just talk about the mass flow rate of the dry air through the system. But then you do the water balance. So it's a mass balance for the water. Okay, how does water come into the system? It's omega on the inlet, and because you could put inlet here, but they don't typically put it there, you just know that omega without any subscript is inlet, because otherwise you just get a lot of subscripts, times the mass flow rate of dry air. That's how much is coming in with the air, the humid air coming in, true? And then you have the mass flow rate of the liquid makeup. And how does it go out? Omega prime, that's the humidity ratio on the outlet, times the mass flow rate of the dry air. You rewrite this equation and you find that the mass flow rate of the liquid divided by the mass flow rate of the dry air is equal to omega prime minus omega. Remember, omega prime is greater than omega, so that's a nice positive quantity. All right. And that tells you what's the makeup requirement to the dry air flow. The hardest one is the energy balance. Okay, this takes tediousness. It'll take a couple pages. I'll have to work through it, but I'll try and do it as efficiently as possible. So on the inlet air, you have mass flow rate of dry air coming in, and then you have the enthalpy, true, of that dry air coming in. The way they write that is they put a subscript A, and it's coming in at the inlet air temperature. I'm going to put an equal sign, and then I'm going to put all the outs on the other side. The mass flow rate of the dry air, enthalpy of the air going out at the adiabatic saturation temperature. That's an out. See those two? So we've taken care of the air. We also have the mass flow rate of the liquid, and it's coming in the liquid form, so it's coming in at H of F at that assumption that it's at the adiabatic saturation temperature. So that's an energy rate flowing in because of the liquid, true? And then we're going to have the mass flow rate of the dry air times omega. What is that? That's now the inlet vapor flow rate, true, coming in, and that's times H of G, and that H of G is at the temperature of it coming in. And then it all flows out in the vapor state, so you have m dot dry air omega prime times H of G at the adiabatic saturation temperature. If you get that equation right, you've gone a long way to get it right, okay? So now what we do is we start rearranging some terms, and so let me just write this. H of A at T minus H of A at the adiabatic saturation temperature plus mass flow rate liquid divided by mass flow rate dry air times H of F of adiabatic saturation plus omega H of G of T minus omega prime H of G of T adiabatic saturation equal to 0. And then we substitute this ratio for this ratio, which is omega prime minus omega. And when you do that and rearrange the terms, you'll get one equation for omega is equal to, in the numerator, you'll have H of air at the adiabatic saturation minus H of air at the inlet temperature plus omega prime times H of G at temperature adiabatic saturation minus H of F at temperature adiabatic saturation, close paren. And then you have H of G at temperature minus H of F at adiabatic saturation temperature. It's not a pretty equation, but it is algebraically doable. And what we want to do is we want to pause and we say, you know what? If I can make an adiabatic saturator, and if I make it long enough so it's coming out saturated air, isn't it coming out saturated air? So it's coming out phi is equal to 100%. Okay? If I can just make a temperature measurement, if I can just measure the outlet temperature coming out, and I can make a temperature measurement of the inlet air coming in, I can infer the humidity going in. I can infer omega. That's a big step. Just temperature measurements in a device where you have, it's an adiabatic saturator, so it's saturated air coming out. and you can infer omega. So let me kind of outline here that omega prime, you need to be able to calculate that, but omega prime is equal to 0.622 PV going out divided by pressure minus PV going out. So the total pressure minus PV going out. And so if it's saturated, guess what PV is? The saturation pressure. It's only a function of temperature. It's a function of the adiabatic saturation temperature. Let me see if I can solve a problem to make this more real. An adiabatic saturator has an inlet temperature of 25 degrees C, and it's always going to be 100 kPa both at the inlet and at the exit. But the outlet air coming out, the TAS, is 20 degrees C. Determine the humidity ratio omega of the inlet air. What is this omega? And then also, what is the relative humidity of the inlet air? That's the big contribution of doing this. Well, equation-wise, it's laid out. Let me do this. Let me try and open up an Excel file. Okay, so let's step through it. The given 20 degrees C adiabatic saturation, 25 inlet air. Specific heat for the air is 1.005. Pressure is known. The saturation pressure at the adiabatic saturation temperature of 20 degrees is 2.34 kPa. And if you notice, if I click here on this cell, you can see that I'm just calling a routine. So if you look at your tables, it may be just a little bit different, but it'll be really, really close, okay? So I'm using the software. And then the dry bulb, not the dry bulb, the dry air pressure is 100 minus that, so it's cell C5 minus C6. And then you compute omega prime. So I know the omega because it's saturated air going out. And then the Hg, you call or look up in a table, H of F at the adiabatic saturation temperature, Hg at the inlet temperature, and you really don't need this one. I don't know why I computed it. It's just garbage. But right there's the equation implemented to calculate the omega coming in, knowing all of those. This equation we've shown. And so the humidity ratio coming in, 0.0128. And then what about the vapor pressure coming in? Well, you can unravel the equation for omega. Let me jump back to here. So we found that omega is equal to 0.622 PV divided by P minus PV. True? Well, if you know omega, you now can calculate PV. It's here and here in the equation. This is P total 100 kilopascals. So PV is equal to pressure total 1 plus 0.622 divided by omega. And that's what I implemented to get the actual vapor pressure right here. So then I can calculate the relative humidity. So it's pretty interesting that two temperature measurements in the adiabatic saturator allows you to infer the inlet air's humidity, relative humidity, and humidity ratio, or calculate them. Okay. So I said that the temperature, this adiabatic saturation temperature, is the same as a wet bulb temperature. Temperature adiabatic saturation is the same as the temperature wet bulb. The temperature wet bulb is really easy to explain. You just need a sling psychrometer, and here's one right here in the box. And what you do is it has two bulbs. One is dry, it's just exposed to air. One has a wick over it. And every semester I got to put a little water on the wick, and so you can feel it. I'll pass it around, and so it's moist. Now, if there's no evaporation off of this, then the wet bulb and the dry bulb are the same temperature, and you can rotate and read the temperatures. But if I sling it around, it's in now a very forced convection state. Okay? And then there's analogy when you take heat transfer between the heat transfer and the mass transfer in a forced convection state. Okay, and so it's evaporating. And if I sling this in a dry room, it'll really drop the wet bulb temperature. It'll be very strong evaporative cooling on that wet bulb. And then I don't have to sling this too long. Then I stop, and then I quickly read. It looks like it's about 64 on the wet bulb in this room, and it's around 74 on the dry bulb. Okay, well, they have a built-in little scale, and all you have to do is, you know, the engineers are pros at this. You have to find this scale is for low temperatures, this scale is for high. You line up the wet bulb and the dry bulb. So I said 74, true. And what was the wet bulb? Wet bulb was 60, what?
64.
64. Okay, wet bulb 64, dry bulb, gotta go right to there. Now it's lined up. Now, a little mark, it's a little below 60% relative humidity. And so I pass that around. So that's a sling psychrometer. $10, that's what that costs. Maybe 20, but if you buy a bunch of them. Now they do have electronics. I have one on my wall. I'm sure that thermostat on this wall has temperature as well as humidity measurements. But this is old school, very mechanical. That's electronics. All right. I want to solve one more problem. Let me get a vote for you guys. Do you have about 15 minutes? Okay. Let me solve this problem then. Moist air at 25 C, 100 kPa, at 70% relative humidity is continually drawn into an air compressor. This is a very practical problem. Anybody ever seen an air compressor? Hopefully you all have. And so it sucks in outdoor air, or wherever, if it's in a building, whatever the room's air is, it's drawing it in. So think of 25 C, 100 kPa, 70% relative humidity. And it boosts the pressure up to, let's say, about 900 kPa. I would say that's, I picked it around 120, 130 psi. So that's very reasonable. That would be the pressure in the tank. And if it just sits in the tank a long time, you have a big tank, it'll really cool down. I know it comes right out of the compressor hot, but if it sits in the tank for a while, it cools back down, and the lowest temperature to cool back down to is the ambient temperature. So just to say, it eventually cools back down to 25 degrees C in the tank before being drawn from the tank, piped over to some shop tools, and used. Because there's a lot of pneumatic tools being run, and like air guns, you know, for removing nuts and the tightening nuts in factories. There's a lot of pneumatic tools out there. So you have a compressor, then basically a heat exchanger, and it sits in this tank for a long time, and then eventually it's drawn off. And so what's drawn in eventually is used. Okay, think of continuously being run. It's continuously running. I know that these things run, then shut off, then run, then shut off, based on keeping the pressure of the tank high, but think of it just continuously running. It is known that the water will collect in the bottom of the compressed air tank. Anybody had experience like that? Yeah. It's a shocker. You'll own a compressor. They'll have a little cock valve on the bottom of that, and they'll tell you need to open that cock valve and drain the tank every now and then. No, that's when you shut it off and the pressure drops a lot, and you're not trying to open it when it's running. They do have automated systems where they have a blowdown, and it'll just go psh, and then shut off. So it'll periodically do a little blowdown to try to keep the tank dry. But if you just own a compressor, it doesn't have a blowdown, you'll have to open up this cock, and the first time you do it, especially on a hot, humid summer day, you're a little surprised. Where did all that water come from? It came out of the air. And with the tools that we studied in this class, we can analyze this problem. So the question is what is the amount of liquid water collected in the tank per kilogram of air drawn into the compressor? You draw in 1 kilogram of air. Let's even call it dry air. Okay? With that dry air, you're going to get some moisture with it. Then it's going to be saturated air here that's going to get drawn off, but you'll get some condensate collect in the bottom of the tank. True? Some condensate. So let's just do a big control volume like this. There's our control volume. We know that there's some work in. We know that there's some heat transfer out. But what comes in is our 25 degrees C and 70% relative humidity air. And what goes out is 25 degrees C air at this pressure is critical. Sorry about that. That's 100 kPa. This pressure is critical, 900 kPa. And the condition of this is it's saturated air. You want to send air to the tools. You'd prefer it to be very dry, but without any dryer system, any desiccant system on it, it's going to send out saturated air, and there'll be some water in the bottom of the tank for this condition. Okay. So what do we do is if you do a analysis of this, you'll say, what is the omega coming in? What is omega? It's how many kilograms of vapor per kilogram of dry air. Well, it's 0.622 PV divided by P dry air, true? So a little bit of work. What is PV? Well, it's phi times P sat at the 25 degrees C. And then maybe you just skip this, just call it the total pressure minus PV, because it like eliminates one little step. Okay? So that's the humidity ratio coming in. My calculations say that this is 0.0141 kilograms of vapor for every kilogram of dry air. Now, what about the humidity ratio going out? State 2. Well, you would do the same thing. You would want to have 0.622 the actual vapor pressure divided by the P minus PV. This P now is your 900 kPa. True? It's our 900 kPa, isn't it? All right. Well, what is PV? PV is 100% of the saturation at 25 degrees C. We could have changed the outlet temperature, but just leave it 25 degrees C. So the vapor pressure going out is 3.17 kPa. And when you go back and calculate this omega, it's 0.0022. Just compare these numbers. 141 versus 22. So the difference is omega inlet minus omega outlet is 0.0119 kilograms of water, which now they're going to have to be condensed. That's where they're going. They're going to go to liquid per kilogram of dry air that goes through the compressor and tank. That difference. So this is the mass of liquid that's put into the tank per mass flow rate of dry air flowing through the tank. So I had this in Excel 2. It's right here. So if you put in 25, 100 kPa, relative humidity, You can calculate all that, and there's the omega. 25,900, that's the big difference. And you have omega very much lower. See that? And the partial pressure is higher. Look at this. The partial pressure of the vapor is higher. It used to be 2.2, now it's 3.17. But the total pressure is so much higher that your omega is much lower. And so that's what comes out per 1,000 kilograms of dry air. You could play around with this. Let's say, oh, I don't think it goes out at 25. Maybe it goes out at 35. Then you can hit return, right? And you see it just changed the results. Okay, somebody says, we rarely have such a humid day in San Antonio, and I think, very rarely is it that hot with that percent humidity. Fine, put it 50%, right? So it changes how much moisture, how much liquid you're going to get into the tank. Some days, if you run air compressor with some tools, like my boys will have a nail gun and they'll work outside. And then at the end of the day, they open the cock, not much comes out. It's a hot, dry day in San Antonio. Okay, but then some days, a lot of water comes out, but it's a humid day. So you can just play with this. There's another feature here is, if it's 25 degrees C and 75% relative humidity, okay, what temperature should you go out at? This, maybe 45 will be where you're driving this to zero right here. Maybe that's 55. Maybe that's 75, Okay, whoops, I went over that. Control Z. 75. Okay, and so that is over that. How about 65? And so what you're doing is, I'm doing a root search by hand. Come up to data. What if? Goal seek. Set that cell equal to 0 by changing this cell. And it comes in at 61.5 degrees C. So if you do supply warmer air to the tools, then it takes more moisture with it. But if you have a shop and you use a lot of compressed air, they'll have a filter dryer system on that compressed air system, or they'll end up replacing a lot of air tools more rapidly. Yeah.